So what I want to do now is I want to try to define what the voltage limit and what the current limit is for the machine, and because that will give us the operating region. And so this equation here that I highlighted, that is the current limit, because the amount of D current that we can apply can't be more than the total IS current. There's a limit. We can the inverter that we are providing to the machine will have a particular rated current. I mean, we can't provide more than that to the machine. So you know, that puts a complete upper bound on the machine operation. Of course, there's a rated current that the machine should be run at, and a peak current that the machine should be run at. So that's really the limit. So you can think of this as the limited current, supply current, and it can be made up of an IQ component or an ID component. And so so now the question is, what is the voltage limit? How is the voltage in the machine limited? And how does that voltage limit for the machine relate to the D and the Q current? Because if we can know the voltage limit and the current limit, then we can understand the operating region that the particular machine we have designed can operate in. So if we look at if we look at this figure here, so we've decomposed the current, and now we could look at the voltage. So the voltage can be the voltage Vs here. That can be split up into a D-axis components and Q-axis components. And so you can read off here what is what. So so the VQ component of the supply voltage will be made up of the ES term plus the ID LD omega term. And here I'm not putting the J on there because I'm saying that whole magnitude there, that whole length has to be these two here. So we don't need to put the J on there. And then the VD in this example here, the ID is going down, and so then but the VS is up, so so this is rotated the other way. So if we want to write this without the J, we need to write it as minus ID LQ omega, because ID would be in the opposite direction. Okay, so I mean, so and ID is down. So then, so this is since in negative Q-axis, right? Because the VD, if we decompose VS, right? VS here has a VD and a VQ. The VD is, looking at the drawing here, is clearly in the opposite direction to the D-axis. It's up. And we've defined Q-axis as positive going down. Oh, that should be D. Negative D-axis. Okay, and then we can note that the Vs squared has to equal Vq squared plus Vd squared. So I'll call that equation 10. Okay, so then So now we can substitute 8 and 9 into 10. So 8, 9 into 10. So then we get Vs squared is equal to ID L, whoops, oh, did I make, I think I wrote something wrong there, didn't I? What did I write wrong? This should be Q, right? Okay. Yeah. So then, so now I can substitute in, so we get IQ LQ omega squared it should have a E to be consistent, the electrical frequency, plus ES plus ID LD omega E squared, and that's equation 11. Okay, now let's divide both sides by omega squared LD squared. So divide both sides by 1 over omega E LD squared. So then we have Vs squared divided by omega E LD squared is equal to flux. Oh no, ES divided by omega LD, not squared, plus ID, and that's squared, plus IQ LQ squared divided by LD squared. That's right. Okay, and then we can note from 2 that the magnetization flux linkage is equal to ES over omega E. That's the flux linkage due to the magnet. So then, and we have ES over omega E, so we can substitute that in. So this is 12. So 2 into 12 gives ES squared omega E LD squared is equal to the flux linkage LD plus ID plus IQ LQ squared over LD squared, and that's equation 12. Oh yeah, 13. Thanks. Okay, so this is a quite a well-known result in machines, and so we'll use this more. So this, if you look at this relates the supply voltage limit to the D and the Q current. There's a square missing. And so this actually is an equation for an ellipse.
So if you say that IS right here is omega m over WE and omega m is equal to ES over W, so they're different. The same equation?
Oh, Did I write that? Oh shoot. Yeah, thank you. That should be... no, that's not right. No, it's supposed to be... It's supposed to be that. Yeah, that's right. And then the omega e cancels, right? Sorry. Did I that's what I wrote, wasn't it? So this is
earlier you wrote it that way.
I wrote it this way?
No, you read it over. You read the way that you had it.
You wrote the division.
Yeah, the division.
Oh. I did. Yeah. Oops. Oh, but I wrote it right for the I wrote it right for the brushless DC motor. And I wrote it. Oh no,
yeah.
no! I wrote equation 2. I wrote equation 2. The equation 2 is right. Yeah, no, but I did. I got it wrong. I wrote it later on. I wrote it again incorrectly. Yeah, sorry. It should be. It should be this because it's the change in flux with respect to time, and so you get omega e times the flux. So then, yeah. So then, if we so if we substitute that in here, then the omega e cancels. That's right? Okay. Okay. Right. Okay. So now, if you recall, thanks for catching that. If you recall, and then I'm not actually I'm deriving this equation. This is the only one I'm not deriving. So if you recall from from DQ analysis, that the torque is given by, and I think we had a homework where we derived this for an induction machine. So the torque can be thought of as the interaction of the whoops, I'm getting all my D's and Q's mixed up here. The interaction of the D-axis flux with the Q-axis current and the Q-axis flux with the D-axis current. This is kind of a little bit esoteric, but if we use this and follow it through, we will get a nice torque equation out. So we can write this in terms of the inductance values that we have, because we can note that the flux in the Q-axis is equal to LQ IQ, right? Because remember, LQ, the definition of inductance is flux linkage over IQ. So that's equation 15, and then the d-axis, the d-axis flux is equal to ES over omega E plus LD ID. So that's the flux term due to the magnet. So this can be written as flux M plus LD ID. And I'll call that equation 16. Okay, so now we can substitute 15 and 16 into 14. So 15, 16 into 14 gives torque is equal to 3p over 2 times magnet flux linkage plus LD ID times IQ minus LQ IQ ID. And call that 17. And then we can rearrange that into, we can collect terms, so we have ID times IQ multiplied by LD minus LQ plus flux M IQ. Actually, I'm not going to give that equation number. I'm going to call this equation 17 because then it matches my notes. So let's look at this for a minute. This is a cool result. We actually got something similar before in electric machine analysis. So, but we used we got this from power equation. So here we have the difference between the L and the D. L and the LD and the LQ, that gives you the reluctance torque. And then this is the magnet flux linkage, which is in the d-axis times the q-axis current. That term gives you the magnet alignment torque. Now, remember what we did at the beginning. We got those saliency ratios, right? And I said that, what did I say? So we had the saliency ratio, which was defined as LQ over LD, right? And so then LQ, when we had a magnet present in the rotor, LQ was larger than LD. That gave a saliency ratio greater than 1. So then if we look here, this is LD. If LD is greater, if LQ is greater than LD, this term is negative, assuming now that IQ is positive. IQ will be positive if it's in a motoring region. If it's motoring. And so then ID has to be negative if you have a salient machine. Otherwise, you will be getting braking. This term will create a braking, right? Because this part will give you a negative value. In order to get a positive torque, ID must be negative because IQ will be positive in motoring. Now let me write that. Note, as LQ is greater than LD. This is for the permanent magnet with the saliency. Remember, when we didn't have any magnet on it, that was not the case that LQ is greater than LD. Note, as LQ is greater than LD for salient pole PM motor, ID must be negative to give positive reluctance torque. Okay. So now, any questions on that? So now we have. So this is the torque equation. This is the voltage equation, and then we had IS squared is equal to IQ squared plus ID squared. That was equation 7. So that is the equation for a circle. So we could plot equation 7 and equation 13, and they will give us the voltage and current ellipses. So 7.7 voltage and current ellipses. I'm going to call them ellipses because a circle is a special case of an ellipse. So this one is a circle because you could, if you remember from circle theory, then you can divide this by IS squared, and that gives you a circle with a magnitude of IS squared. But if you, on this one, because in this one it's more complicated because we have an ID and an IQ. I think I'm missing I think there's a squared term here, right? Yeah. If you could look at equation 11, there's a squared term, but it didn't disappeared on equation 12. If you look on your notes, there should be a squared there. Sorry. Okay, so then this has got IQ squared and ID squared. There's also this term here, which is creating an offset in the circle, in the ellipse. But it's an ellipse because the coefficient for if you've got rid of this term, the coefficient for the ID and the coefficient for the IQ would be different because of the LQ over LD squared part here. So what we have is we could plot this on an ID and an IQ axis. So this is ID and this is IQ. So we have a circle that is the current limit, and that has a magnitude of actually I should do it over here. That has a magnitude of IA, and this is the Q-axis, and so this is the gamma. If you look at the definition of the vectors, if gamma was 0, then the current would be aligned only with the Q-axis. And if gamma was 90, the current would only be aligned with the D-axis in the negative direction. Okay, and then we also have this voltage limit, and that then creates an ellipse. And that's an ellipse, and it would be centered at a point that is governed by this this magnetizing flux divided by the LD, flux M divided by LD, and that is a that is a special. It's a very special term, which is given a name of characteristic current, so we can call that IX. And so that term, the magnetizing flux divided by the d-axis inductance, so that is the numerator is dependent on the rotor magnetization, and the LD is dependent on the inductance, which is related to the rotor and the stator. So it's a characteristic. This ratio is a characteristic of a particular machine. And so the point where these two intersect is the operating region. And so in this picture here, there's not much of a region that you can operate in. So, this is the voltage ellipse. And I'll talk more about that in a minute. So this is governed by equation 13, and then this is the current circle, and that's governed by equation 7. Now, so this is a little bit complicated when it's an ellipse. It's hard to draw ellipses. So let's just for this last bit of discussion here, let's assume that LD is equal to LQ. So we'll go back to having no saliency and look at these limits, because it still is quite interesting, and it's easier to draw circles. So if LD is equal to LQ, then we get a circle for the voltage limit, but the circle will be offset from the center line by the characteristic current value. So if LD is equal to LQ, then we get Vs squared divided by omega LD squared is equal to ID plus flux linkage LD squared plus IQ squared. So then the question is, how do these voltages and currents relate to the operation of the machine? So let's so in this, I'm going to run over slightly, so I don't mind if you leave. I'll post the video. So I want to it'll be another 10 minutes, so I'm going to explain. So I want to explain how the voltage limit and the current limit relate using this handout that I gave you, because it's so much easier having a picture. So if LD is equal to LQ, then the torque equation simplifies down as well, and so the reluctance torque disappears. The understanding of the voltage and current ellipses or circles can be understood without having this term in there. So I'm doing that again because it's easier to make circles. So we have, so if LD is equal to LQ, then the torque is equal to 3 over 2 P times the magnetizing flux times IQ. Now if we, so then, and so if this is the, so now thinking about only the case where we have LD is equal to LQ, what would be the value of the ID current that maximizes the torque? So remember that the ID, the current is limited by equation 7. So if IS is fixed, then, and the torque is only dependent on IQ, we would like to, if we want to maximize the torque, we would like ID to be 0. So to maximize, and this is the case if, again, this is the case if LD is equal to LQ. To maximize torque per amp, the ID should equal 0. Okay, and so remember that the speed, the mechanical speed, is related to the electrical speed by P over 2. Okay, so then if we look at this, if we look at this equation here, we can see that this actually defines the diameter of our circle for our voltage limit. As the speed, as omega m speed increases, omega e increases, and so therefore this term becomes smaller. That means that the ellipse shrinks as we increase our speed. So let's look at this briefly, and again I think it's just going to be 10 more minutes. Right. So in this picture here, I have drawn so this is the q-axis. Let me know if you can't see that, and I'll make it bigger. And then this is the d-axis. So this could be the IQ and the ID. And so this circle here is the current limit circle, and so that would have some current value IS, and so then there's the gamma, and so this is just the current limit circle. Right, okay, IS squared is equal to ID squared plus IQ squared. Okay, and so if we're in motoring region, then the motoring, the top half is the motoring quadrant, or the top two sides, because that's where IQ is going to be greater than 0. And then bottom is the generator quadrants. And so these circles here are these 4 circles are for different voltage limit circles. So I could number these 1, 2, 3, and 4. And so they correspond to different speeds. So these are the voltage limit circles for the particular machine, and therefore different omega m values, where the omega m1 would be smaller than omega m2. So 1 is the 1 circle corresponds to omega m1, and then omega m3 is smaller than is greater than omega m3 is greater than omega m2, and then omega m4 is greater than omega m3. So now again, if you look at the if we look at the equation, you can see that on the left side of the equation, that as omega as the denominator increases, then these circles will shrink in size. So you could think about what happens if you are at the omega m1. What that means if you're at omega m1 is that the voltage limit circle fully encloses the current limit circle, so you can operate anywhere within the current limit circle because they both overlap. Okay, and then so that would then mean that we could, if we were to look at the torque speed curve, so torque speed curve, then we could be, say, at this operating point here. So we could get a large torque because we could apply the current IS at its maximum value, which would also mean that the IQ which would also mean that the IQ here is at its peak value. And then but then we keep going. We want to go faster, and so the speed increases. That means that the circle shrinks in size, and so then but we want to have peak current, and because we want to have peak torque. And so this point here with the dot is a special point because that is the maximum on the circle. That's the maximum value for IQ. That's when ID is equal to 0. And you can see at that point, that's where we can maximize the torque, but we cannot operate at this point if our voltage limit circle drops below this point. So this is a special point. This is point A. And so that on the torque speed curve would be right at the end of the constant torque region. Constant torque. So now if the speed increases further, the voltage circle will reduce in size, and so it might come down to 3. And then what we have to do then is that we can no longer operate at A. We would have to travel, if we want to maximize our torque, we would need to stay on this outer limit of the circle, and we would move down the edge of the circle to this point here. So that's the point that we can get the maximum torque out. But in order to be at that point, we have to supply the current. Remember, as a magnitude, IS squared. That has to now have a component of negative D current as well. Now, what does that mean with regard to the magnet flux if you have a negative D current? That means, remember, the positive D is flux going out. So this point here means that we are applying a current in the negative direction with respect to the d-axis flux. So we're creating a demagnetization flux. So we are reducing the flux. So because remember, E, the voltage, is the induced voltage from the rotor is a function of the magnetizing flux times the speed. So if we want to reduce down EA, we need to apply a current in the negative direction, and you can see that if you look at the way that the d-axis flux was defined. If it's equal to this. So we need to apply a ID current that's negative. That will then reduce down the EA, and that's what this is doing. So we'd be somewhere like here, B. This is B. And this would be omega M3, and this is omega M2. And then if we keep going faster and faster, we get to this point here, and this is at this point we have no q-axis current. We only have a d-axis current. We have no torque at this operating point. But the circle is not zero, and that's actually inconsistent with the equations that I showed, because the circle should get to zero if you look at the equations. However, the equations that I wrote out neglected the resistance in the wires, and so you would always have some circle size. So this is actually, this would go down to zero here, a zero torque. But so then you should have a, if you looked at our equations, this should go to 0 point as well. But I've still kept a circle here to be realistic, because we'd have resistance, but I didn't include that in the equations. Okay, and so the IS current would stay constant throughout, but the ID current would be going down, down, and down till IQ. The IQ current would be going down. So now, if you had saliency, then this would not be quite right, because we would have to we'd be having the combination of the ID and the IQ going on. Any questions on that? Just let me write a couple of points, and then that's call it a night. I wanted to say here, let me. Well, probably I don't need to. I was going to write down what I said, but I think I probably you're probably okay with that, right? Okay. Let me just say one more thing then. I said that this point here, see this offset, this is an offset here. This is Ix, which is the magnetizing flux divided by LD. Okay? Just think about that for a minute. So Ix is equal to the magnetizing flux divided by LD. If we could make a machine where this characteristic current point here was always within the current limit circle, what would that mean? So because remember that because it's shifted out, we get to the point where we can't have any more torque. So if you could, and remember that both of these terms are dependent on how the machine is designed. So if you could shift this characteristic current to overlap with the current limit circle, then you would have a machine that has infinite constant power speed range. The machine could keep providing some torque at indefinite speed, and that's something that's really of interest to automotive industry, because then you could still provide torque at really high speed. So that's a open research topic question that people are still studying. So I'll let me write if point Ix can be shifted to overlap with current curve limit, then this would allow motor to have an infinite constant power speed range, CPSR. That you can search on that. There's lots of people talking about that, and this limit was only I think derived in the 90s. Okay, I'll stop there, and thank you for putting up with me.